Thank you for the announcement. So, so we resume our morning session with the subtalk of this morning. So who will be by Hans Ringström from KTH and Institute Mittag-Leffler, and who will talk about geometric perspective on cosmological singularities.
Okay, thank you very much. And let me also start by thanking the organizers for this wonderful workshop. It's a pleasure to be here in Edinburgh. Enjoy the beautiful weather, right? So, yeah, it's fantastic. So this talk is about cosmology. So the first slide, I just very roughly want to set the stage. Right? So the standard models in cosmology, they're spatially homogeneous and isotropic. So the main point is that there aren't really any preferred spatial regime, right? So asymptotic flatness is not a natural condition in cosmology. And so that gives you a rough idea of what you should think in the spatial directions. So what about time? So when you study isolated systems, and I suppose also nonlinear evolution equations more generally, people are typically interested in geometries with some sort of time translation invariance. I'm not interested in that because that's not so natural in cosmology. So in cosmology, it's quite natural to imagine that you have a space like Cauchy hypersurface, the mean curvature of which is bounded away from zero. That's a non-zero constant. This is quite a natural situation to consider. And in that situation, Hawking's theorem applies. I mean, depending a little bit on matter content, but Hawking's theorem applies. And it tells you that you have incomplete causal geodesics. Right? And one can interpret that as a singularity, at least Hawking and Penrose would, even if Michaelis doesn't, right? And then you can ask yourself the question, what is the nature of that singularity? So that's really the question in cosmology. You expect typically that there will be a singularity. What is the nature? Now, this is something that it's, of course, very hard to sort out in general, and I'm certainly not going to be able to do that, but that's sort of where we want to go, even if we're so far not able to go there, right? And there are many types of singularities. I will be mainly interested in a special class here, which are the so-called crushing singularities. So the point here is that there is a partial foliation of the space-time, space-like Cauchy hypersurfaces, and the mean curvatures of these space-like Cauchy hypersurfaces is diverging to infinity, right? And I will then, this divergence, I will sort of interpret that as some sort of singularity. So this is the general setting I'm interested in, and I want to understand. But let me start by something simpler. Let me start by sort of the standard models that physicists like these days, right? So they like spatial homogeneity, and they like spatial isotropy, and these days they actually even like spatial flatness, right? So this is what you like. And the matter content is typically consists of orthogonal perfect fluids with some linear equation of state and a cosmological constant. And usually you would like to have two fluids, so dust, which would model ordinary matter and dark matter, and a radiation fluid. Now, if you go towards the singularity for scaling reasons, only the radiation fluid will be relevant, right? So you can forget about everything else. I should say, I mean, of course, cosmologists also like inflation. So I will sort of skip that for the moment. I might return to that a bit later, right? But if you look at these matter models, then it's the radiation that's going to dominate, right? So then a very basic question you can ask yourself, if you look at a spatially homogeneous and isotropic and spatially flat solution to the Einstein radiation fluid equations, is that stable in the direction of singularity? Right? So that's a basic question you can ask. Now, in order to, for that question to be meaningful, you have to consider a situation which is more general than spatially homogeneous and isotropic. So the simplest way to go beyond spatial homogeneity and isotropy is to drop the isotropy. So I still insist on spatial homogeneity, I insist on spatial flatness, but I drop the isotropy condition, right? And then, but in order to describe this in more quantitative terms, I need to parameterize the anisotropy in some way, and that's the purpose of the next slide. So, and I should point out that this slide now is completely general, is not associated with any kind of symmetry or any specific background solution. So I'm just here assuming I have a crushing singularity. Oh, okay, this does. So you have a crushing singularity. So I remind you that this means that I have a partial foliation by space-like Cauchy hypersurfaces, the mean curvatures of which diverge, right? Okay, and then what I can look at is this Weingarten map of the leaves of the foliations. Okay, so what is a Weingarten map? I hope most people are familiar with the second fundamental form. And you can think of the second fundamental form as a symmetric covariant two-tensor field induced on the leaves of the foliation. That's fine. If you just raise one index with the spatial metric, right, you get a 1-1 tensor field. It's called the Weingarten map. So I mean, this is effectively just a second fundamental form, right? But this is now viewed as an operator on the tangent spaces of the leaves of the foliation. That's how I want to think of this object, right? Now, due to the assumption, the trace of this operator is diverging uniformly to infinity. So if you want to extract some meaningful information from this, it's natural to normalize the Weingarten map in some way. One naive way to do this is to just divide by the mean curvature. So this gives this what I call the expansion normalized Weingarten map, and this will be actually the main character of this talk, this rather simple object, right? Okay, so what can we say about this? Well, obviously, this operator is symmetric with respect to the induced Riemannian metric. So it has real eigenvalues. So you have n real eigenvalues, and by the normalization, they sum up to 1, right? Okay, so this is clear. And in 3 + 1 dimensions, the eigenvalues are just summarized by 2 functions then, right? I mean, you can take, since the sum is 1, you can just look at L plus L minus, right? Now these numbers, again, I want to emphasize, this is not at all related to background solution or symmetry or anything like that. This is just a general observation. And these numbers then give a measure of anisotropy. When L plus L minus are 0, that's sort of isotropic situation, non-zero, non-isotropic situation, right? And I mean, so when they're 0, this means that the expansion normalized Weingarten map is the identity map divided by the dimension. Okay, so this is to parameterize sort of anisotropy. So now we can return to the question. So, so now I'm looking at the state space for Einstein radiation fluid, spatially homogeneous, spatially flat, but not non-isotropic. So now there are 3 degrees of freedom. So there's the omega, which is an expansion normalized version of the energy density of the fluid. And then there's L plus L minus, which, as I said, sort of describe the anisotropy. But then there's also the Hamiltonian constraint, which restricts you to this half sphere, right? And where is the isotropic solution sitting in this picture? Well, the isotropic solution is the North Pole. Well, as I said, L plus L minus is 0. That's isotropic. So North Pole, that's the isotropic solution. And at the base of the half sphere, you have a circle called the Kasner circle, which parameterizes the Kasner solutions that Spiros was describing yesterday. Right? And what are the dynamics on the state space? Well, it's indicated by the arrows. So if you start, F is a fixed point, so then you stay there. But if you start close to the fixed point, but not on the fixed point, you will go down the half sphere and you will end up at a point on the Kasner circle, right? So in the direction of the singularity, the isotropic solution is unstable, right? So this is unstable, and you move towards the Kasner solution. In this setting, the Kasner solutions, though, are stable. Right? And now you can ask yourself the question, what happens if I now perturb these Kasner solutions? So I admit some spatial curvature, right? So in this setting, they're stable, but this is a very restricted setting. So let's say now that, okay, I still insist on spatial homogeneity, but I do no longer require spatial flatness. What happens then? So then the picture becomes like this. So let me relate the 2 pictures. So you see here is the L plus L minus plane, and you see this circle. The circle is the same as at the base of the sphere, right? It's this Kasner circle, right? So in both cases, this is, yeah, they're the same. Okay, so what happens if I take a point S on the Kasner circle? This represents a Kasner solution. Say that I perturb it now and I admit spatial curvature. Well, it's unstable, so you move away from this point, but you move away in a very specific way. So you follow a straight line, in fact. So you take the closest corner on the triangle. So you see, I mean, it's inscribed in the triangle. You take the closest corner of the triangle, you draw a straight line from that corner up to S, and then you just continue until you hit the Kasner circle again. Right? So this is the dynamics. This defines a map, kappa, from the Kasner circle to itself, called the Kasner map. Right? So you get this map from the Kasner circle to itself. Okay, so then you end up at kappa of S. Well, of course, this is also unstable. If you perturb that, well, then you will go on to kappa square of S. That's also unstable. You go to kappa 3 of S, and so on and so forth. Right? So now you see that S1 with this map kappa, this is, of course, just a one-dimensional dynamical system. Right? And the properties of this one-dimensional dynamical system is quite well understood. This is a chaotic system. So you have this chaotic behavior, right? This is what you expect. Okay, so that's unpleasant, but it gets worse. So the point is that, of course, this is just like in the spatially homogeneous setting, you get this type of picture. But in general, in the spatially inhomogeneous setting, you expect, I mean, if you believe in this sort of, that you have space-like singularities, then you expect sort of each observer going to the singularity will experience its own chaotic dynamical system, right? So I have infinite number of chaotic dynamical systems going in towards the singularity, right? So it's a rather messy picture. Okay, can you get away from this? Can you avoid this? Well, yes, so let's go back to this. If you would, instead of insisting on a radiation fluid, you insist on a stiff fluid. So this means that the pressure is equal to the energy density, or equivalently a scalar field, then you get the same state space, but there are no dynamics. So all the points are fixed points. So it's the same, but all the points are fixed points. Okay, so in this big picture, they're all stable, but this is, of course, still the spatially flat setting. Right? So that's what happens if you now admit some spatial, some spatial curvature. What happens then? Well, then some of them are still stable, but some of them become unstable, and you get this picture instead. Right? So this is now then projected down to the L plus L minus plane. So the points inside this triangle, they remain stable, but everything else is unstable. And there is an important recent result by Grigorios Vonodavlos and Igor Rodniansky and Jared Speck, proving that these solutions are stable in the direction of the singularity. Right? So this picture is fine. Okay, now, but you can also, of course, in practice, you can imagine, if you look at the real dynamics, you can imagine a combination of these things, right? So you start with like a radiation fluid, you move out to the Kasner circle, you bounce around a bit, but if you have this stiff fluid or a scalar field, when you bounce around, you're not going to make it all the way to the Kasner circle because the matter content is actually monotonically increasing during the dynamics. So it's going to increase, so you're going to move, you're going to bounce before you hit the circle, actually. And so you're going to move towards the center of this disk. In the end, you're going to end up in this triangle, and then you're going to settle down. This is sort of a more complete picture. Okay, fine. So this gives you some idea of sort of spatially homogeneous dynamics somehow in the direction of the singularity. And let me perhaps say something about PDE aspects, just linear PDE on cosmological backgrounds, and more specifically, let's return to the Kasner solutions that Spiros already introduced to you yesterday. So you're now very familiar with these, right? So this is the metric GK. This manifold MK. If you prefer to have it on Rn instead of Tn, that's fine too. And in order for this to be a solution to Einstein's vacuum equations, then you have to have these Kasner relations. So the sum of the pi and the sum of the pi squared is 1. Now, in this case, you can calculate the mean curvature. The mean curvature is 1 over t. So t equals 0 is a crushing singularity, clearly. And if you calculate this expansion normalized Weingarten map, then it's going to be this k, which is actually constant. And so, in fact, in this case, you see that actually these pi characterized in the Kasner solution are actually the eigenvalues of this expansion normalized Weingarten map, right? So they have sort of a natural interpretation here. Yeah. Okay, and then there are special solutions which Spiros threw away yesterday, and I will also throw them away today. So if one of the PIs equals 1, then all the other ones have to equal 0. And then these solutions are space-time flat. So these are quotients of parts of Minkowski space, and you actually get a Cauchy horizon, and you can extend the solution beyond the Cauchy horizon, and then you get closed time-like curves. This is not what I want to discuss today, so I'm going to throw those out, right? Okay. Now, if you want to look a little bit more closely at this geometry, a natural thing to do is, I mean, if something is contracting, you have a singularity, it's natural to just blow it up, right? And the natural way of doing that is just you take the metric, you multiply by the mean curvature square. This is quite a natural thing to do. It's been done by many people before. I like the work of Arthur Fisher and Vince Moncrief, which maybe you're not familiar with, but I can recommend. Then they certainly do this. So if you carry out this operation for the Kasner solutions. So you multiply by the mean curvature squared, and at the same time, you change the time coordinate. Here it sort of looks a little bit arbitrary. I take minus the logarithm of t. I mean, it seems rather random. Point is that t it's the volume of the leaves of the foliation, right? So taking the logarithm of the volume fits very nicely together with the mean curvature, right? So this is, I mean, geometrically meaningful more generally, right? So I'm doing this construction here in a very special case, but it actually makes sense more generally, right? Okay, so then the conformally rescaled metric then looks like this, and this metric has several features which sort of correspond to essential properties of the singularity. So as Spiros was saying yesterday, you have space-like singularity. So observers going into the singularity lose the ability to communicate. And this sort of corresponds to this exponential expansion, right? So you start with a metric which, is a singularity, things contract. But from this perspective now, actually the space-time expands exponentially, right, in the direction of the singularity, the conformally rescaled metric, right? So you have exponential expansion, which is nice. And the exponential expansion really captures the space-like character of the singularity, the fact that you lose the ability to communicate, right? So that's an important feature. It also has a nice feature if you look at the expansion. So if you look just at the Weingarten map of this metric, it's actually constant, and the eigenvalues are the beta i's again, right? So that's quite nice property. And of course, if you want to solve wave equations, I mean, it's quite nice with an exponentially expanding geometry, right? So that's quite nice. Okay, so right, so let's just very quickly, if you look at the wave equation on this background, so the wave equation on the Kasner background, so this is gk, not g hat k, right? I'm interested in the end, I'm interested in the Kasner. Well, then this is what the wave equation looks like, right? So at least if you're naive about it, I mean, this is very simple to analyze, right? I mean, there's some exponentially decaying factors in front of the spatial derivatives. Let's throw it away and solve the equation u tau tau equals 0, right? We know how to do that. And actually, that is essentially the whole story, right? I mean, this is how solutions behave. You get a homeomorphism between regular data and initial data, in fact. No, sorry, initial data and asymptotic data even, right? So you can do that. And I mean, let me just say, I mean, there's general theory that covers much more general systems of equations, but generally of this type, right? And yet, let me just very quickly say some features of this general theory. You quite often get sort of like homeomorphism between initial data and asymptotic data. And a slightly more sophisticated analysis might give you an improved regularity of the limit of u tau. So the leading order behavior is the limit of the u tau. And actually, in some situations, you get that the limit of u tau is more regular than the initial data. Right? This is a little bit interesting. It would be interesting if one can exploit this, but anyway. And even though this looks nice, you can actually add first order terms. So say e raised to minus gamma I t ui. where gamma I is strictly positive, then you would think, well, then you can just throw away first order terms. But actually, if the gamma i's are strictly less than the beta i's, generic solutions grow super exponentially. So like e raised to t, right? So that's a little bit funny phenomenon, right? And I should also say the methodology can also be used to analyze the case which is somewhat less obvious, namely when tau goes minus infinity, where the factors in front of the spatial derivatives grow exponentially. That can also be analyzed in detail. You can get like a homeomorphism between and asymptotic. So there is a general theory here, not the main point of this talk. Okay, so this sort of finishes the introduction, so to speak, to this talk. So I've said something about spatially homogeneous cosmology and sort of dynamics, and also something about like wave equations on these types of backgrounds. Now I want to describe a framework for sort of a framework for crushing singularities, right? And this framework involves quite a lot of assumptions, and these assumptions are certainly a restriction, but they're motivated by the fact that a lot of solutions where the asymptotics are known in detail, they satisfy these assumptions, right? So I'm just going to describe this framework, which in practice means I'm just going to describe a large number of assumptions that I'm going to be making, right? So bear with me here. There's going to be quite a few slides of assumptions, and it's not going to be complete either, but okay. Right. Right. So as I said, I'm interested in crushing singularities. So I have partial foliations by space-like hypersurfaces, space-like Cauchy hypersurfaces, and the mean curvature diverges to infinity. Actually, in this framework, you can sort of deduce this from other assumptions. So that's not the main assumption on this slide. The main assumption is rather that the volume density goes to zero uniformly. That's the main assumption I want to make on this slide. So what do I mean by that? Well, let's just put a reference metric. So G bar ref, that's a reference metric on this M bar. And then if you do that, you get, of course, you get a volume form, mu G bar ref, that's a volume form, right, on M bar. But for each leaf on the foliation, so for each M bar T, you of course also get an induced Riemannian metric, G bar. So you get family of Riemannian metrics, G bar T. And they have associated volume forms, so mu G bar. And of course, these volume forms are related by a smooth positive function, which I'm here denoting e raised to this rho. So rho is for me now the logarithmic volume density. And the main assumption I want to make here is that this object then diverges uniformly to minus infinity, right? So that's quite a lot of examples satisfy this. This is not this assumption. So you can think of then this logarithmic volume density as sort of measuring distance to the singularity. And sometimes I will say that assume that things decay exponentially. What I mean by that is that things can be estimated by e raised to epsilon rho, where epsilon is some positive constant, right? So this gives you some sort of rate of convergence in the direction of the singularity. So that's what I'm assuming. One advantage of this object is that it doesn't involve any derivatives of the metric as opposed to the mean curvature, right? So that's also an advantage. Okay. So just like in the case of Kasner solutions, it's natural to conformally rescale the metric by just multiplying by the mean curvature squared. And I'm going to assume silence, or this is sort of like space, another way of saying space-like singularity in a sense, right? I mean, when I say silence, the thing to have in mind is just that observers going into the singularity, they lose the ability to communicate. So in the end, asymptotically, there is silence. You can't communicate, right? So that's what it means. Okay. And what the assumption I'm making here is that the Weingarten map of this conformally rescaled metric is negative definite with a constant bound, right? Okay, you may be a little bit, surprised now when you compare what I said for Kasner, because then the Weingarten map of the conformally rescaled metric was positive definite, actually, right? But in that case, I also reversed the time direction. Here, I've only conformally rescaled. I didn't reverse the time direction. So here, it's negative definite. There, it was positive definite, right? But, okay, beyond that, it's sort of the same. Here, I'm also interested in the non-degenerate setting. So I'm actually going to assume that the eigenvalues of the expansion normalized Weingarten map are distinct, and that there's actually a fixed, constant lower bound of the distance between the eigenvalues. So I'm going to make this assumption. Okay, So in this sense, in this setting, so you have the eigenvalues of the expansion normalized Weingarten map. They're ordered like this, right? And of course, then you get eigenvector fields associated with this XA, and normalize them to have length 1 with respect to the reference metric. Now, these need not be global, right? I mean, there can be an obstruction to having global fields like this, right? But if you just take a finite covering space, everything will be fine and you'll get global objects. So I'm going to just assume that you take a finite covering space if necessary. So then these are global objects. So you have a global frame like this, and then you can complement it by U hat here, which is just a future directed unit normal with respect to the conformally rescaled metric, right? So then you get actually a frame on the space-time, which is these XA and the U hat. And let me, I don't know how familiar you are with the different aspects of three manifold topology, but let me just point out that on closed three manifolds, oriented closed three manifolds, they always have a global frame, right? This is not a topological restriction, right? So just to point that out. Okay. Then lapse and shift. So lapse and shift are defined by this relation, and the additional condition that chi, which is the shift vector field, is actually tangent to the leaves, right? So that's sort of fixes n hat and chi. And for the framework to work, chi need not be 0, but for the particular, I have one particular application in mind, and in that application, I'm going to assume chi equals 0. So let's assume that the shift vector field is actually 0 here, to start with. And then the only assumption beyond that I'm making is that the lapse function is strictly positive, which isn't really much of an assumption, right? So, okay. And now we come to bounds. Okay. Right. So now maybe I should say a word or two, right? So what's the point, right? We ask ourselves this question every day, right? But anyway, so anyway, so what I find looking at lots and lots and lots of examples of spacetimes or you know, singularities, cosmological singularities, there's one feature which to my mind is very surprising. And that is that this expansion normalized Weingarten map is bounded. It's bounded on convergent settings, it's bounded in you know, chaotic oscillatory settings, it's bounded in lots of different settings. And a priori, there's no reason whatsoever why this object should be bounded, right? There's no reason, right? And so the entire point of this framework, or the motivation for me, at least, was, well, if it's always bounded in all these different examples, then you can ask yourself the question, what mileage can you get out of assuming that it's bounded, right? Let's assume that it's bounded, and let's see what can we deduce from that, right? So this is sort of the motivation for developing this framework in the first place, right? So the main object I want to bound is this expansion normalized Weingarten map, and in some suitable weighted Sobolev or sort of CK spaces, right? So let me perhaps unpack this a little bit. So G bar ref, that's the reference metric. D bar, this is the Levi-Civita connection associated with the reference metric. So that's okay. And then, but then I'm putting a weight here. So K, the expansion normalized Weingarten map should be bounded, but it's fine for me if the derivatives go to infinity in the direction of singularity. That's fine, but they shouldn't go to infinity too quickly. So some sort of polynomial rate in this logarithmic volume density, right? So that's what the weight is here, right? So I'm assuming these types of objects are bounded. Of course, it's not enough to assume only that the expansion normalized Weingarten map is bounded. I'm also going to have to make some sort of assumptions on the lapse, the normal derivative of the lapse. This is the expansion normalized normal derivative of the expansion normalized Weingarten map, right? So this is also, you have to put some sort of bounds on this quantity. And then also something, you need to have some control of the spatial variation of the mean curvature. So just for reference, okay, let's what happens for the Kasner solutions? For the Kasner solutions, the first quantity is 0, the second is constant, the third is constant, the fourth is 0, the fifth is 0, and the last is constant, right? So that's for the Kasner solution. But these bounds are satisfied by, you know, lots of examples, right? So it's not just a very simple example like the Kasner solution. So okay, so this sort of okay. And then there's a final, rather technical assumption here, which, I mean, okay, this is a bit more harder to justify, perhaps. Right? So there are certain off-diagonal components of this expansion normalized normal derivative of the expansion normalized Weingarten, right? So certain off-diagonal components here that should decay exponentially, right? And so if you're in a situation where you have convergent behavior, you actually expect the whole thing to decay exponentially. For Kasner, this object is identically zero, but this sort of condition is even satisfied if you take, Bianchi 9, where you have chaotic oscillatory dynamics. This condition is actually still satisfied, right? So it's satisfied in interesting situations. Okay, so this is the framework. So what you get out of this framework? So there are several things you can use this framework for. So first, if the geometry is like this, you can actually analyze the asymptotics of solutions to systems of linear wave equations on these backgrounds, right? So that's one application of this framework, or what you can do if you have these assumptions. So here, X is a matrix of vector fields on the space-time. Alpha is a matrix of functions on the space-time. Needless to say, you need to make some sort of assumptions concerning these coefficients, but let me just say, I mean, so the conditions are general enough that, for instance, I mean, if the coefficients converge at all, the limits need not be continuous or anything like that, the limits of the coefficient. So you can really get, when you go towards the singularity, you can get radically different behavior, exponential growth or decay, depending on the specific spatial point where you end up. So you really need to localize your analysis to, like, you take a causal curve going into the singularity, you take the causal future of that, and you need to analyze behavior in that type of region, because it will, if you just move around the point on the singularity where you end up, you're going to get radically different behavior. So it's general enough to handle that type of situation. And I mean, you whatever framework you develop, it certainly should be general enough to handle that type of situation, because that's the sort of situation you actually expect, right, on a cosmological singularity, that you can get radically different behavior depending on the spatial point. So you also get sort of a geometric perspective. So you can isolate a specific parameter which will, so a scalar function which will sort of tell you whether you should expect these oscillations like this Kasner map, right? So you can extract a specific function, right? And this also gives you like a unified picture of many of the solutions where the asymptotics are known. So you give a unified and understanding for why the dynamics are the way they are, right? And also you can sort of extract enough information to get a natural sort of notion of data on the initial data on the singularities. I mean, this is something people have studied for many years, right? So partially it's not at all new, but partially, I mean, it gives also, again, a unifying perspective on many results. Okay, so these are some applications of this framework. I'm just going to limit myself to one specific application in this talk. And the specific application I have in mind is that, so you want to identify a convergent regime somehow, right? So we have this beautiful result by Greg and Igor and Jared, right? Where you have stability of these Bianchi type 1 solutions. Now, it's of interest to identify some sort of convergent regime, which is not related to being close to a specific background solution, that there is a regime that you can describe geometrically, and that if you're in this regime, you expect convergent behavior, and you also want to derive asymptotics that are detailed enough that you get really data on the singularity, where you can hope, in best case scenario, to go in both directions, right? You get data on singularity, and perhaps you can start with those data on singularity and go the other direction, right? So this is sort of what I want to describe. So then, of course, okay, so I need to make more assumptions. So to describe those assumptions, so first, let me introduce Q. Q is very important. It's the so-called deceleration parameter. And it's just defined by this relation here, right? So of course, if Einstein's equations are satisfied, you can calculate Q in terms of matter quantities and geometric quantities, right? So this is, but this is of crucial importance. But the main assumptions I'm making, so here I'm just going to restrict my attention to the Einstein scalar field equations. And the main assumptions are these two inequalities that I've labeled one.
If it's very important, you can remind, maybe theta is the mean curvature, right? And it's a lapse. What is U hat? I forgot. What is U hat?
Okay, U hat is a future directed unit normal with respect to the conformally rescaled metric.
Okay.
So yeah, so it's 1 over theta times the normal derivative as the normal vector. Yeah.
There's no lapse there, right? It's just the dimension.
No. And it's the spatial dimension. Yeah.
Oh, I misunderstood.
It's not. Yeah, it's not lapse. It's the spatial dimension. Yeah. Okay. Right. Okay. So the assumptions I'm making are these, right? So what about, okay, let's start with the second one. In 3+1 dimensions, this corresponds to being inside the triangle I draw earlier, right? I mean, so in the L plus L minus plane that you're inside, or if you will, this corresponds to the expansion normalized Weingarten map being positive definite equivalently. So in 3+1 dimension. And that in that setting, the condition is necessary. You have to be there, otherwise it's not going to work out. You're not going to get convergent behavior. And this is just an analogous condition in higher dimensions, which was suggested quite some time ago by Henault and co-workers, right? So, but this is now, okay, this is now, you can phrase this condition without reference to any specific background solution, right? So this is just you can use this to identify a convergent regime, right? The first condition is a little bit more questionable, perhaps. So in the case of the Kasner solution, that Q is equal to, well, so in the case, the example I gave first with the half sphere, and n equals 3, Q equals 2 just corresponds to being on the half sphere somehow, right? So that's what it corresponds to. But here I'm making an assumption that this quantity is decaying exponentially. And this you should think of here as some sort of bootstrap assumption, because at the end of the day, what you can do is you make this assumption, and at the end of the day, you can prove that you get the same type of estimate, but with a better decay rate, actually. In that sense, it's sort of like a bootstrap.
Okay, but geometrically, is it something like CMC, or that you're?
Well, no, I mean, okay, yeah, okay. So it's going to be related in the end, I suppose, right? But I mean, but strictly speaking, it's. I mean, so of course, yeah, it's not. That's going to behave quite nicely also in the end. I mean, the spatial variation of the mean curvature. Okay. Right. Okay. So what do you get in the form of conclusions here? So then you can conclude that actually this expansion normalized Weingarten map is going to converge to a limit. Right. So I assume that it was bounded. It converges to a limit, and I'm denoting the script K, and then, in fact, also the eigenvector fields converge to a limit, the eigenvalues converge to a limit. And this, of course, is related to the fact that I put a constant lower bound on the distance between the eigenvalues, right? So, okay, these things happen. So I get one piece of geometric information on the singularity, which is the limit of the expansion normalized Weingarten map. So that's nice. Okay, can we get more geometric information? Well, let's rewrite the metric according to this 2a, right? Here, this isn't anything deep. 2a is not deep. So as long as the shift vector field is 0 and the mean curvature is positive, you can certainly rewrite the metric like that, right? I mean, that's just some trivial rewriting. So there's nothing deep about this, right? What is a substantial conclusion, though, is that then you extract these B bar AB, and these objects actually converge to a limit, which is diagonal in a sense. So these R bar A, these are functions on M bar only, right? B bar AB are functions of both M bar and time, right? But these objects are converging to a limit. So if you sort of, you can, I mean, this part, the sum here, this is the spatial metric, of course, right? So this is a metric on the leaves of the foliation. And essentially, this is characterized by the B bar AB in a sense, right? So you can instead write this H check, right? So this is now a family of metrics on M bar, which essentially, I mean, up to theta, contain the same information as G bar, right? You can go back and forth if you wish, right? And then you can define this H bar, which is effectively a metric on the singularity. This is, so H bar is a Riemannian metric on the singularity. And what this is telling you is that H check is converging to H bar. So you have a family of Riemannian metrics on the leaves of the foliation, which contains equivalent information to the induced metric, but this one actually converges, right, to a limit. So a limiting Riemannian metric on the singularity, right? So you're extracting a Riemannian metric on the singularity.
Sorry to trouble them, but just to understand, it seems to me you're allowing your background to be oscillatory. But
Well,
then
no, in this case, not, right? I mean, now, so okay.
you said your assumptions are satisfied by Bianchi 9, for example.
Not this
Not
one.
that one. I see.
Right?
I see.
So I mean, I went, you know, with this application. So as I said, I gave the general framework. Now I'm going to a specific application.
I see.
And in the specific application, I want to describe a convergent regime. So now,
Okay.
no oscillation.
Okay.
No oscillation.
Understood.
Okay. Right. So fine. So you extract. So we extracted the script K, which is like second fundamental form on the singularity. We extracted H bar, which is a Riemannian metric on the singularity, right? And then you can also deduce asymptotic information for the scalar field. So phi bar A and phi bar B, which is essentially data for the scalar field on the singularity, right? So what you end up with is really, so you have M bar, H bar, script K, phi bar A, phi bar B, right? This is, and so this I'd like to think of as data on the singularity. And these actually satisfy certain relations. So first, by the normalization, trivially, the trace of script K is 1. Script K is also symmetric with respect to H bar, which is quite nice. Then you have sort of what survives of the Hamiltonian and momentum constraints. That's these two relations. And then, okay, by the assumptions and the eigenvalues of script K are distinct. So you get these sort of data on the singularity, and there are good reasons to believe, but okay, I mean, there's no proof of this at this point. Well, in the real analytic case, actually there is, right? So you can actually go in the other direction. Starting with data like this, you can produce a solution with these asymptotics, right? So in the best of all worlds, you could actually get a homeomorphism from data on the singularity to solutions in a sense, right? I mean, modulo various obvious complications, right, with this. Okay. Right. And then, I mean, just to summarize, this is sort of the relation between the solution and the asymptotic data. Okay. So, okay, I'm about finished actually. So just to discuss this specific result, what are the advantages? So the advantages here is that, I mean, it's like a partial bootstrap assumptions where the conclusions, you strengthen the assumption. So it's that, in that sense, it's like a partial bootstrap argument. That the result isolates a convergent regime without any reference to a specific background solution. This is not a stability result, right? I mean, it identifies a convergent regime where you can hope to prove sort of Big Bang formation. Okay, and the asymptotic information that you obtain is strong enough that you can hope to get like a homeomorphism between data on the singularity and actual solutions. So that's nice. But this result also has a fundamental disadvantage in that, yes, you get stronger conclusions, but there is a loss of derivatives, meaning that you cannot actually close the loop. Right? So there is a fundamental problem with this, right? But it gives you an indication what to hope for, but it doesn't, take you quite all the way to where you want to go. But let me just finish by saying, so this is just one application of this framework. There are lots of other applications of this framework. And with that, I thank you for your.
Other questions or comments?
What are the other applications of this framework?
Well, I mean, it's like I described before, right? I mean, analyzing the asymptotics of linear wave equations on this, getting this geometric perspective on the bounces. I mean, so let's see. So for instance, another conclusion you get out of this. So I mean, you remember, so the Kasner map, right? So you have the Kasner map, and now, so this all takes place in the L plus L minus plane, right? And so a crucial question you can ask yourself is, okay, so how do these L plus L minus evolve? And in this framework, you can actually calculate this. So let's sort of, let me try.
Taking away the assumption that did not allow us.
Yeah, exactly. Yeah. That one's gone now, right? Okay, so this is what you get. So you see, okay, the dots are things that, you know, decay, you ignore them, right? Okay, so then you're left with these equations. So this U hat was, again, the expansion normalized, I mean, the normal future directed unit normal with respect to conformally rescaled metric, right? Okay, that's U hat, right? And so this tells you, how do L plus L minus evolve, right? That's a crucial question you want to know. And I mean, certainly you expect to bounce around. Now, and what you see here is that, well, there's one parameter determining whether you're going to move at all or not, and it's this. And S bar is the spatial scalar curvature. So it's the spatial expansion normalized spatial scalar curvature. You divide the spatial scalar curvature by the mean curvature squared, right? But you see here that actually you will travel along a straight line, right? I mean, you see from these equations, right? This, you're going to go along a straight line. And what is this straight line? It's the Kasner mount, right? So this also comes out of this framework without assumption of symmetries or anything like that. You do reproduce the Kasner mount. It just comes out here, right? And you can also identify sort of the quantity. Okay, this, yeah, maybe we discussed this, but I mean, you can actually identify also exactly what a specific scalar quantity that determines. So then, so the question is, if this is non-zero or not, right? So if you're inside this triangle, then this thing just goes to zero exponentially, and therefore you're not going to move, right? But if you're outside the triangle, this will pop up, so to speak. But there are specific functions which, if they're non-zero, you will get dynamics. If they're zero, you will not get dynamics. And this is then related to, for instance, like, well, spikes also, for instance, right? This particular function you can calculate somehow. So, but this is also can be explained rather geometrically in terms of the eigenvector fields of the expansion normalized Weingarten map, right? So that's, yeah.
Sure.